Okay, so you might be saying to yourself, well, what about our confidence intervals for one population mean if the standard deviation is not known? Which seems like it would be a likely kind of thing, especially if we're working with a sample. Well, if we're going to deal with a sample, let's talk about what that would mean to us. What we're going to have to do is we're going to have to modify our approach a little bit. And one way that this was modified was using something called a standard normal curve, but modifying it based on the sample size. And we call that a T distribution. So the standard normal curve and the T curves shown right here are different. In green, the standard normal curve represents what happens if we have a population size that's normally distributed and we know something about the sample size being relatively large, greater than 30. Now, if we decrease that sample size to something less than 30 and we don't know the standard deviation of the population, we adjust that using something called a degrees of freedom. And for example, in this case right here, we can see that our degrees of freedom, 6, means that if we have a sample size of 7, we subtract 1 from that sample size and we use degrees of freedom 6. Now you're saying, well, why would we subtract 1? If you recall, way back when we were talking about finding standard deviation, one way that we did it was we said that the standard deviation for a sample, S, was equal to the square root of, we took the sum of the differences between each x value and the sample mean squared, and divided that by n minus 1. See a familiar pattern right here? That's right. N minus 1 is our degrees of freedom. So we take our sample size minus 1 and we get something called a degrees of freedom. And that's an important topic to us because we want to make sure that we're getting the right curve to represent the probabilities that we know. Now this T curve, sometimes we call it the student's T curve, named after a statistician by the name of student. That was his name. It's not because we're giving it to students, so don't feel traumatized or anything like that. The studentized version of the sample mean, suppose that X has a population that is normally distributed with a mean of mu. Then for samples of size n, the T value is going to be equal to the sample mean minus the population mean divided by the sample standard deviation divided by the square root of n. And it has a T distribution with n minus 1 degrees of freedom. Now you'll notice that there is a family resemblance here between the T value and the Z value, right? Remember from our normal distribution, we would say that the Z value in our last discussion would have been something more like x bar minus mu divided by the standard deviation over the square root of n, where standard deviation was the standard deviation of the population. The difference is S is our sample standard deviation. Right? So this T value is based on the set of values that come from this curve. There are some properties of the T curves. First of all, just like in the Z, the normal distribution, the total area under the T curve is equal to 1. A second fact is that the T curve extends infinitely in both directions, approaching but never touching the horizontal axis as it does so. Again, just like the Z curve. The T curve is symmetric about 0. Again, just like the Z curve. And finally, as the number of degrees of freedom become larger, the T curves look increasingly like the standard normal curve. Well, that is actually the principle of our central limit theorem, which states that as our sample size increases, then the sample size, the distribution is going to approach what we would expect for a normal distribution. So once we get over size 30, then we would say that we should use our Z distribution instead of our T distribution normally. All right, where could we get them? Well, one way of getting our T values is from the table. There is a T distribution table, and the way that we read it is it's based on our degrees of freedom, which is in the left column, and the right column, and our alpha value. We look for an alpha value in a single tail, or alpha over 2 value in a single tail, and try to find a distribution value based on that, right? This is a t value. We treat it just like a z value from our tables. We're going to use Excel to do this, however, and let's use Excel to work out this example. Pickpocket offenses. The FBI compiles data on a robbery and property crimes and publishes the information in a population at risk rates and selected crime statistics. A simple random sample of pickpocket offenses yielded the losses in dollars shown in the table at right. Let's use Excel to find a 95% confidence interval for the mean loss mu of all pickpocket offenses. Pardon me. Well, our table contains 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 25 samples. So our sample size 25 is going to have a degree of freedom of 24. That would be important if we're looking that up in our table. But let's go to Excel and show how this works out. First of all, we're going to find our mean. For our offenses right here, right, the loss in dollars is shown. So we're going to get our mean. Equals average. Wow. Equals the average of these values right here. So the mean loss is 513.32. Our standard deviation, well, this time we're going to get the standard deviation directly from the sample. So you go STDEV, and we have to use the one that says .S for samples. And we take our sample standard deviation. There it is. And we get that standard deviation. Now, we might suspect that there could be an outlier right here. 1064 is pretty much above, pretty high above that mean, but it might or might not be too high or too low. We would have to compare our samples. We're only going to do this once, though. So our MBE, how do we find it? Well, because we're going to have a small sample, less than 30, in which we don't know the standard deviation from the population, we're going to go ahead and use a t-distribution. The way it works is this. Equals confidence, and you'll see the one right here, confidence dot t. It says it returns the confidence interval for a population mean using students' t-distribution. Our alpha is just like the alpha level before. Because it's a 95% confidence interval, we take 1 minus 0.95 and get 0.05. Our standard deviation is the one that we found here on the table. And our sample size is 25. Where there it is, 108.24. Now the lower amount is going to be our mean minus the MBE and the upper is going to be our mean plus the MBE. No, not D2. That's a mistake, huh? E2, right? That's our mean plus our MBE of 108.244. There it is, 621.564. So our confidence level is that the actual population mean based on our t distribution is somewhere between 405 and $621. All right, so that's pretty good right there. That's our confidence interval, and it works essentially the same way that our confidence level did for our normal distribution. The only difference is the kind of function that we're going to use. Now, in this modified version right here, I cut out the very highest and very lowest. If I suspect that there is an outlier, one method of handling that is to just simply ignore the very highest and very lowest values. And in this case, that's this very high one and this very low one. So if I did the procedure, and you guys can do this procedure too for yourselves, this is our standard deviation and mean, and we would find our information based on that down here. Okay. Don't forget the assignments that are due this week. By Friday of the 7th week, please make sure that you've watched the Chapter 8 lecture. And by Monday of week 8, this should be week 8 also. Good Lord, boy, I'm having a good day, huh? Complete the Chapter 8 web assigned homework and complete online quiz 4. And other than that, thank you all very much for your kind attention. Have a great week, everyone.